Okay, we hear this. So welcome everyone. I have the pleasure to start this semester's game theory seminar series. I'm going to talk about computing balance solutions for large international kidney exchange programs. I hope that there will be at least a little bit of something for everyone. There's going to be kidney exchange and matchings and some cooperative game theory and some simulations. This is joint work with Peter Biro, Walter Ken, and Daniel Paulusma. And we would like to dedicate this to Walter, who sadly recently passed away. Okay, so first, I'm going to talk about kidney exchange modeling, how we model kidney exchange programs and how we put this into an international setting. Then I'm going to focus on two particular main issues of choosing initial fair allocations that we would like to find a suitable matching for. And how do we choose that suitable matching? Finally, I'm going to talk about some simulation results. So the way I'm going to talk about kidney exchange is completely out of the context of diseased organ exchanges. This is all living organs. And the situation is that kidney patients, their best solution for a recovery is through a transplantation with a donor. Today we're going to talk about living donors here, and that situation means that patients arrive to a kidney exchange program with a willing donor. However, many of them have between the patient and the donor. Quite often there are incompatibilities. This can be blood type or tissue type incompatibilities. Therefore, they are not necessarily a good match for kidney transplantation. However, there is a possibility of two pairs of kidney patient donors to exchange their donors and create two pairs of compatible patient donor pairs. This can happen through pairwise exchanges. It can happen a three-way exchange or larger circles as well, or through an altruistic chain started with a donor. For our purposes, the way we model a kidney exchange program is that we have a compatibility graph. This is a directed graph with arc weights W, where the vertices are the patient donor pairs. And there's an arc from one patient donor pair to another if one patient's donor is compatible with the other patient, and that patient's donor is compatible with the former patient. What we are looking for, an exchange cycle is a directed cycle in this compatibility graph, and an exchange scheme is a union of pairwise vertex disjoint cycles. And our goal is to find an exchange scheme with the total weight of exchange cycles being maximum, with a bound on the length of these cycles for logistical reasons and for many other reasons. We cannot deal with exchange cycles of arbitrary length. So this is bounded by parameter L. This is the standard kidney exchange program. And the way we put this into an international setting is by partitioning the vertex set. The set of patient donor pairs are partitioned for the countries. So we have n countries, each of them control a set of nodes in this compatibility graph, their patient donor pool. And with this setting, we have an additional goal in mind, is that we have to find a way to ensure the participation of countries. So we need to find a way to convince them that this is actually beneficial for all countries. Obviously, we're not the first one to work on this problem. Just a snapshot of the most recent, most relevant literature. Carvalho and Lodi worked on this in the pairwise exchanges setting, so when L equals 2. And they had a 2-round scheme where they were able to compute Nash equilibria efficiently. Sun, Trudeau, and Walsh, they were similarly focused on L equals 2, and they had lower and upper targets on how much a country should, how much kidney transplants should a country receive, and they formalized fairness as they are trying to maximize the minimum of these lower and upper target ratios. Klimentova and others, they extended their setting to freeway exchanges as well, but it was limited to 4 countries. And they introduced a credit system that we are going to use as well. And they compared the potential and the benefit value against each other as a chosen allocation to target. And they concluded that the benefit value behaves somewhat better. Biro, Peter, and others, they worked in a similar setting with just 3 countries, compared the benefit and the Shapley value, and concluded that the Shapley value behaves better. And our probably most relevant predecessor is also Biro, Peter, and others. They focusing on the, again, pairwise exchanges. What they shown is that if we trying to find a matching that a maximum weight matching with arbitrary weights that minimizes the largest deviation from a target value, that problem is hard. However, if we're looking for maximum size matching such that we minimize the largest deviation from a target, that problem can be efficiently solved. And we basically extended this result, again, focusing on pairwise exchanges with not only minimizing the largest deviation, but lexicographically minimizing the deviations from a target allocation that we would like to meet. We performed simulations in the largest scale that we have ever seen, extended it to up to 15 countries, and we try to introduce some of the classical, more sophisticated allocations, such as the nucleus. So our assumptions is we're dealing with pairwise exchanges, L equals 2, and we're looking for maximum size matchings instead of maximum weight with some arbitrary weighting. The reason why this is reasonable is that there are some countries where the exchange cycle is legally bound to be 2, such as France and Hungary, for example. And in most European exchanges, there are a variety of criteria that they are looking for, and almost always the top criteria is to perform as much kidney transplants as we can do. So these assumptions seems to make sense. And we crucially need it because there is a substantial difference from L equals 2 to L equals 3, as well as maximum size and maximum weight.
But what is the case if you have only 2 weights, 1 and 2? So perhaps the weights are not so well measured, so there are good times and bad times. So
That is a really good question, and it's important from practice as well, because the way we set the weights to be one is just we only care about the number of transplants, and the compatibility graph allows us to do a transplant if there is any possibility of making it. However, we can distinguish that there are situations where if we desensitize a kidney, then there is a possibility of making an additional transplant. So a weighting would absolutely make sense, such that there are easier or more valuable matches than others, but there are two possible ways of doing it. On the top of my head, I cannot tell whether we can extend all of our results to that setting, but we are definitely looking into that. Thank you very much. Yeah, Peter?
Special case where we have only two kind of weights. It's not that we have that. We are actually, that was actually one to a well-known matching program, which is still undecided how hard is that. So in that case, we can find an exact answer for this question. If we have two weights, but with really different weights, it's already not.
Okay, thank you very much. Under these assumptions, we can simplify our directed compatibility graph to an undirected graph where between two nodes, there is going to be an edge exactly if there is an arc in both ways between the two nodes. And now I'm going to talk about the credit system that we're going to use. In European exchanges, typically European exchanges are being done in rounds. Like we have a national or international kidney patient donor pool, and we run a matching, find a matching to find suitable transplants every 3 months, let's say. So if we have n countries in an international kidney exchange program, then let's suppose that in round H, we have mu H as the size of the maximum matching in the compatibility graph. And we're looking for an allocation. The allocation itself is going to count the number of transplants we do, not the size of the matching. So there's a 2 multiplier here. And let's suppose that we are given an initial fair allocation Y that we're trying to find a matching for. We're trying to find a matching that provides the shares of the countries as a given fair allocation. And we're going to have a credit function as well in order to make up for our deviations through the round from this initial allocation. So once we're given an initial allocation Y, and we have some credit values, some deviations some past deviations from the previous rounds, deviations from this fair allocation, that is going to be our target allocation. And when we are looking for obviously a maximum matching in the compatibility graph, and we are going to obviously count how much transplantation is prescribed to a country by that maximum matching. That will be the S values. Once we have chosen our matching in round H, we can get a new credit function for the next round, which is nothing else than the difference from the target. And I forgot to point out, of course, credit values are going to sum up to 0 so that we just redistribute. And by that, if X is an if Y is an allocation, then X is going to be an allocation as well. And similarly, in the next round as well, since over all countries, we are going to distribute the size of the maximum matching. Okay, once we have the credit values for the next round, h+1, we get a new fair initial allocation, yh+1. That means we have a new target, x, and we're going to find a new matching and so on and so forth. So now I'm going to talk about, there are two particular details that we have to care about. One is how we choose what is a fair allocation that we would like to meet. And the other is how we choose the maximum matching that fits our target the best. So first, we're going to talk about initial allocations, and this is where cooperative game theory enters the picture. This is standard TU game stuff. We have player set that will going to be consisting of the countries. These players form coalitions, and for each coalition, we determine a value by the value of the characteristic function. We assume that the grand coalition value is maximum over all partitions of the player set, which is actually going to be the case for the games that we are interested in. And we would like to divide this grand coalition value in some fair manner. And for that purpose, we are going to focus on generalized matching games introduced recently. This generalized matching game is a cooperative game on an undirected graph that will be the compatibility graph with a partition of the node set. Each player or country controls one set of nodes. And introducing the notation for a coalition, just taking the union of the nodes that the players in the coalition control, we can determine the coalitional value V of S as the maximum weight of a matching in the subgraph induced by these nodes that the coalition controls. So indeed, we do get a generalization of the classical matching game if the partition we choose is the atomic partition where each player controls exactly one node, we get back the classical matching games. What kind of fair allocations we could consider? While the allocation part of this is clear, we're going to divide exactly the grand coalition value among the players. We can talk about core allocations where there is no coalition who would benefit from breaking away from this cooperation to form their own coalition. And we are interested also in the access values that measures the difference between what an allocation X provides to a coalition and their expectation based on the characteristic function of the game. If we order this these exponential many access values non-decreasingly and lexicographically maximize this vector, we get the unique allocation of the nucleus, provided, of course, that we do the lexicographical maximization over the set of imputations, which again is non-empty for the games that, in case of the games that we're interested in. We can be interested in the Shapley value as well as a fair allocation, which is nothing else than the expected value of the marginal contributions of a player joining a coalition that she is not a member of. These are well known and what I would call, at least today, the sophisticated allocations that we could be interested in. Somewhat less sophisticated, or in another way, easy to compute allocations we get if we observe that obviously there is a surplus. There can be a surplus in a game if the imputation set is not empty. The grand coalition value minus the sum of the values that the countries or players would achieve if they would act on their own. And if we get an allocation, if we distribute this surplus among the players in an arbitrary fashion, whichever weights we would like to prescribe. We get the benefit value as introduced, as defined by Klimentova and others recently. If we use the following weight, we sort of felt that that we felt a little bit more comfortable with another weighting. So we introduced the contribution value. The only difference is if we take a look at the contribution value, it is clear that the weights are based on the contribution of a player to the grand coalition value, whereas it's not necessarily intuitional why we would adjust that with the singleton coalition values. But nonetheless, it's a possibility. So these are the solution concepts that we are going to employ to generate fair initial allocations in the kidney exchange program. Yeah.
So these values consider a case when we have separate countries and they want to join, but perhaps in practice it is more common that we already have an international cooperation between countries, and some other countries want to join this coalition.
Yeah, that's a possibility.
Maybe there are similar situations, and in this case, perhaps there are other solution concepts make more sense because we have a coalition that already exists. And
like at a first glance, I don't see why you wouldn't treat that in a similar coalitional setting. I mean, so you say that there is a possibility that some countries are definitely cooperating.
Yes, and so there is a coalition that already works, and you should persuade this coalition that they can.
Yeah. Certainly, so if that previous cooperation is set in stone and there is no possibility of another country entering, and just because there is another option on the table, that cooperation would break up, then just you can treat them as a player in this, at least in this setting, with a larger pool, and then you can. And from a more practical point, so obviously with kidney exchanges, there's a lot of law and ethics behind it. So it would be a strange situation if an agreement is likely only going to happen if everybody is treated in a fair and equal manner, whatever that means. So yeah, I don't know how this specifically would work in practice, but what I can imagine is that there is a possibility if another country is there, then most likely I would think that, at least especially in this setting, we are looking for the largest cooperation possible because it's beneficial for everyone, hopefully. And if that doesn't happen, then I don't know what happens, because it's not entirely impossible that then there is an entirely different cooperation arises from that. I hope that answered that question. Okay, let's take a look at an example to put this into context. We have an international kidney exchange program of 3 countries over 2 rounds. In round 1, this is our compatibility graph on the left, and on the round 2 is the one on the right. In round 1, the node I1 is controlled by the first country, I2 and I3 controlled by the second country, and I4 is controlled by the third country. We start from credit values being 0, and let's consider the Shapley value. We build the generalized matching game based on this compatibility graph and compute the Shapley value, we get these values as a fair allocation, something that if we believe in the Shapley value, this should be the number of transplants each country receives. Obviously, that's impossible, but nevertheless, we can try. We're looking into the maximum matchings, and we find there is a unique one. And this unique maximum matching prescribes 1 transplant for country 1, 2 transplants for country 2, and 1 transplant to country 3. So in the next round, our credits are going to reflect the fact that we missed these fair values. We went a little bit over in the second country, and we are a little bit behind on the first and the third country. So we have some credit values that adjust that. And in the second, of course, in the second round, I should sum up this part as well. The first I1 is controlled again by the first country. I2 is controlled by the second country, and I3 is controlled by the third country. We build a generalized matching game. We compute the Shapley values. We get a target value. And among the 2 possible maximum matchings that we can choose from, we picked one choosing this edge. And then our credit values are going to be 0 at the end. Whereas if we do the same with the nucleolus, round 1 is completely the same. Round 2 is going to be a little bit different because the nucleolus is different from the Shapley value in round 2. Therefore, our target is a little bit different, but the matching, let's say we chose the same matching and we end up with some non-zero credit values after round 2. Okay, so now I'm going to talk about how we are going to choose those matching once we have the target value. First of all, there are two mindsets of optimization we could take. One is D1 that is existing already in the literature. Let's minimize the largest deviation from the target value. And our approach is minimize the largest deviations lexicographically. So given a target allocation and a generalized matching game, if we would like to minimize the largest deviation, this is the problem that we have to solve. This is being done, we're looking for a matching solving this problem. And this is being employed in the literature. However, what we suggest is, let's take a look at given a matching and an allocation, the non-increasingly ordered country deviations, the vector of non-increasingly ordered country deviations, and let lexicographically minimize that over the maximum matchings in the compatibility graph. That is going to be the problem that we are interested in. How we are going to solve that problem? We are going to rely heavily on a theorem which says the following: if we're given a generalized matching game and a set of closed intervals, one for each player in the game, we can find a maximum matching such that the allocated well, for our purposes, is going to be allocated kidney transplants, but the nodes covered by that matching is going to be in that closed interval for every player. And this can be done in polytime. This theorem is the idea is based on enlarging the current compatibility graph and find with some introducing additional nodes and additional zero weight edges, and finding a maximum weight perfect matching that will determine whether is there a matching that these S values are matching the closed intervals we are prescribed, or there is not, or there is none. And this can be done in polytime. Okay, as we will see in a minute, we are going to need to deal with open intervals as well, not just closed intervals. That is not a huge problem because these S values are integer. So whenever we have an open interval, we can replace it with the largest integer endpoint closed interval that fits into that, and then we can apply this theorem. Okay, so this is the algorithm to find a maximum matching that lexicographically minimizes the deviation from a target allocation. Let me just quickly guide you through. It's quite simple. Given a generalized matching game and an allocation, first we compute the smallest deviation such that it bounds the deviation of all countries. And we find a maximum matching that achieves that. Once we have the smallest deviation, we're going to minimize the number of countries receiving that deviation. Actually, the smallest, largest deviation. So the worst deviation, the number of countries receiving the worst deviation are being minimized. And this is where we're going to need some open intervals. And then we're going to just, and once we done step 2, we can fix the deviation of countries in set N1. We're finished with them. And then we just have to repeat this until we fixed the deviation of all countries. And the output is going to be the matching that lexicographically minimizes the deviations. And our main theorem is that given a generalized matching game and an allocation, with this algorithm, we can find a lexicographically minimizing maximum matching in polynomial time. Now, I don't want to go into the proof heavily into, but I thought at least I'm just going to talk a little bit about the sketch of the proof. So the output, let M over line be this maximum matching, the output of the algorithm, and M star is a lexicographically minimizing maximum matching. In particular, we chose a lexicographically minimizing maximum matching that is as close to our output as possible. What do I mean by that? Being these maximum matchings, we can find even alternating path between these two matchings, so that these are the paths that they are that is the difference between the two matchings. And I'm gonna call M star closest the lex-min matching that is closest to M over line, our output, if the number of paths is minimal. The part that is easy to show is that the largest deviation, the value of the largest deviation is the same for the lex-min matching and the output. And it's also easy to show that the countries receiving this largest deviation under a lex-min matching is not part of the same for the output. So there's a country P0 in this set, which means that M star prescribes a deviation of D1 star for this P0 country, whereas our output prescribes something smaller. At this point, we have to distinguish between two cases of the absolute values, but the two cases are completely similar. So I'm only gonna talk about the first one, and I'm gonna talk about it in a moment. Just before that, once we finish with this, what we have to do is a very similar analysis for dt star being equal dt, and nt star being equal nt for every t up to n. And in terms of the running time, since the allocation x is given and the S values in the deviations are somewhere between 0 and the size of V, the node set, the number of nodes divided by half, it means that we can search this value in log number of nodes. And in order to do that, we have to call this theorem, or the modification of this theorem, that is being done in number of nodes cubed time. So this is the time it takes to find and fix one dt value. And every time we do that, there is at least one country whose deviation is fixed. There are n countries, and this is how we get the final running time. Okay. Very quickly browsing through how we are going to deal with this case. So in this case, for the P0 country, which is in N1 star but is not in N1, it means that M star is actually providing more kidneys to P0 than our output, which means that there is a path from starting from a node in P0, a node controlled by P0, starting with an M star edge, and finishes at P1 controlled by, finishes at a node controlled by country P1 with an edge in the output matching. In case P1 country is also favored by M star, then we can find another path from P1 to P2. And what we can also show that these are P1 and P0 and P1, we can show that these are different countries. P0 and P2, not necessarily, they can be the same, but in that case, we already finished with the proof because we found a lax-min matching that is closer to our output than M star. Eventually, at some point, because these are maximum matchings both, we're going to find a country PR such that the output favors country PR to M star. In this case, consider the matching M dash that is exactly, we start from the lax-min matching and we change it over these paths. In this case, we have an upper bound on the number of kidneys prescribed by M star, which can be a strict upper bound depending on whether country PR is in N1 or not. What we also know about how the lax-min matching and M dash treats country PR. It's exactly one difference. So we also have a lower bound. And we also know how they behave on country P0. We know that exactly, we're not only finding a bound for that, but we know that exactly. This M dash matching is also a maximum matching. It is also closer to our output M over line than M star. So at this point, all we have to prove is that M dash is lexicographically minimal, and we get the contradiction we are looking for. And since we observe that on countries not at the end, at the beginning, at the end of this series, M dash and M star are symmetric. At this point, either M dash is lexicographically minimal and we're finished, or PR must be in N1, so we know exactly how M dash treats that country. And observing also that if that is the case, then M star and M dash are treating P0 and PR symmetrically, so that we just have to switch the two countries and we get the deviations. This eventually leads to M star being lexicography minimal, and this proves that N1 star equals N1. So at least in the first iteration, the output of the algorithm the output of the algorithm provides the same result as a lexicographical minima matching. Now all we have to do is repeat this for all t's, and we're done. Okay, on to the simulations. We generated 100 compatibility graphs using William Patterson's very useful web tool, replicating real kidney exchange data. And we considered the 4 allocations that I mentioned today, and we considered international kidney exchange programs under the following scenarios. As a baseline, we took a look at what happens if there is no cooperation. Next, we can take a look at what if the maximal matching is chosen arbitrarily. So we don't do any optimization on that part, which practically means that we're not even trying to hit any sort of target. What we can also do is minimize the largest deviation without adjusting from round to round with credits. So all we care is every round we're given a Shapley value. We're trying to get as close to it by minimizing the largest deviation. We can do the same with adjusting it with credits. And we can do lexicographical minimization with or without credits. So very briefly about what happens without cooperation. This is done roughly in a 2000 node graph. So about 1/3 of the patients are treated without cooperation. What is more notable is that no matter what kind of cooperation we are doing, this is going to lead to, unsurprisingly, a significant improvement. At the same time, the number of transplants we manage to do does not really matter what kind of scenario or what kind of allocation we're looking for. It's always going to be something like 1.8 times. How do we behave in terms of errors, in terms of deviation? So in these graphs for the 4 allocations, where on the horizontal axis we have the number of countries ranging from 4 to 15, I included the arbitrary matching as well. And these are the 4 lines distinctly above the others, hovering around 40% of relative deviation. Whereas the other 4, D1 or Laxmin with credits or without credits, are all on the bottom. So let's just zoom on to that bottom part to see what's happening. Here, what we see is that, again, unsurprisingly, credit values are useful. So the 2 lines on there is a gap between whether we use the credit values or not to balance out the program. And also there is a gap between whether we do D1 optimization or we do Laxmin optimization. There is also a seemingly consistent order of allocations. The Shapley value produces the smallest deviations. If we use the best scenario or best policy that we can choose for our program, Laxmin optimization with credit values, then that leads to 0.52% relative deviation from the targets. And this is 0.81 for the benefit value, 1.1 for the contribution value, and the last came the nuclear levels, 1.23. Now one could walk out of this room with the takeaway that the Shapley value is the best, and it's pretty obvious. The way I understand these results is that a policymaker has to decide what is a fair allocation that we believe in. And if someone would believe that the nucleus is the fair allocation, I would say that 1.23% relative deviation is not terrible. So the way I see it is that as long as we make the right policy in terms of using lexicographical minimization and using the credit values, just choose the fair allocation that you believe in. Otherwise, things could get grim. Looking at under LexMin plus C scenario, looking at the 4 allocations a little bit closer, the only notable thing that we can see here is that up to 12 countries, actually the contribution value is worse than the nucleus, and there is a change at 12 countries for some reason. And the reason why I say that this is important to focus on LexMin optimization and the credit values rather than the actual allocations, which is, I'm not saying that we shouldn't focus on that. I'm just saying that is a different conversation. And based on the computational times, what we see is that this improvement of switching from D1 to LexMin is pretty much comes from free. It's not even surprising because we have a polytime algorithm. So it should be almost for free. And I see that the total computational times in a single instance is negligible. These times actually are initially dominated by that we have to build a large graph. But of course, after a while, generating the exponential large cooperative games is going to take over. So there is an exponential explosion in the game generation, which, by the way, does not affect the contribution and the benefit value because they only rely on n+1 coalitional values, or actually the benefit value is 2n+1, but it doesn't really matter. So this is my justification why LexMin is important, and the reason why I hammer this that much is for some reason the literature were always focused on D1. What about the credits? While theoretically it's possible that we cannot find a matching that is as suitable to our target value as we wish, and credits are just keep on being accumulated. The simplest way to imagine that is, first of all, if the maximum matching is unique, and as we increase the introduction of different weights, this is more and more likely, then there isn't much optimization to be done in the first place. And if this happens to be in a situation like we saw in the example, where there is some positive credit values and that compatibility graph would repeat itself infinitely over the rounds with a unique maximum matching, then of course credits are just keep on being accumulated. So we looked into whether this phenomena appears in our simulations or not. Again, on the left side, I have the arbitrary matching scenario included, and we see that, yes, and on the horizontal axis now we see the periods. This is a 6-year program with quarterly matching, so we have 24 periods, and we see that with arbitrary matching, credits are just keep on piling up. For the other 4 scenario, again, it's hard to distinguish. So again, let's zoom in on the right side for the Shapley and the nucleus. It's easier to see with the nucleus, but these shapes are completely different for all allocations. we see that indeed, there is no credit accumulation if we employ the credit system. So the two stable lines, Laxmin plus C and D1 plus C, are stable and balanced. However, we can see that even though the arbitrary matching is just crazy, Laxmin and D1 also show a slow buildup of credits. So this, again, justification of why we need one part is Laxmin, why we need the credit system as well. And this is pretty much the same for the other two allocations as well. These figures that I picked up, I picked is particularly focusing on 15 countries, but these shapes are entirely the same for no matter what size of the countries that we chose. Okay, so I'm going to conclude now with our main. Well, the main message is to use taxonomical minimization in the credit system and choose the fair allocation according to your beliefs. And their contributions to the literature is providing a polytime algorithm to finding this Laxmin matching so that it's possible. We conducted large-scale simulations in a scale that has never been seen before, introduced some other sophisticated solution concepts that is also new in this literature. Our paper just became available on arXiv. We are very much looking for comments and questions if you're interested. And also the codes are available in GitHub if you want to play with them. Some references, and thank you very much for your attention. Any questions? Either in the room or online.
A small question from online, if it's possible.
Yes.
I will switch on my camera, and then you can also see me. When I understand correctly your story, you say you have a certain round, and in that round you make the allocations. But in that round, if I understood correctly, are the number of donors fixed, in fact, so the number of patient donors, so the number of nodes is fixed. It's not.
Yes.
So I was wondering, because you said these rounds are taking place once in 3 months. In practice, you say, when it is done more often, you get more dynamic question also perhaps involved here, which you get, because then it's interesting perhaps that some kidneys which you are allocate in the first period, in the first round, would be better to allocate in the next round because it has a better fit, in fact, in the next round. Is it something you considered or you're thinking about? Perhaps you have to, I don't know whether the audience here has a question.
Yeah, just let me repeat the question for the people in the room. So the question was, in each round, a matching is prescribing some kidney transplantations, and we do those transplantations, and those kidneys and patients, they leave the system. And the question was whether should a country consider the possibility of some kidney being more useful in the later rounds. And we looked into that particular setting as well. I believe the literature calls this the ideal scenario. What would happen if countries could actually foresee their, well, the reason for the quarterly matching is that some new patients arrive, some patients leave the system not being treated by this matching. They might be able to get a diseased organ donor, or unfortunately other things can happen as well. So there is a dynamic part that countries cannot deal with. But if you could foresee what would happen, well, we looked into that, and what I can say is that in terms of practice, this is something very hard to play with. And the conclusions in terms of how the different allocations behave, what we are aiming for, or how the different policies differ in terms of D1 or lax minimization. These are replicating pretty much the same, just on a higher scale, because they can make smarter decisions.
Yeah. Okay. Thank you.
Thank you very much. Any other question? Honestly, Marty, this question is just like if we discuss that. Okay, you're gonna ask this question, right? Let's look let's have a look what happens after. So, yeah, we looked into varying size. So the baseline is every country size is the same, and we try to play with what happens if we introduce different country set sizes. We just took small, medium, and large. And it seems that some values are a little bit, like on the graph, some lines are a little bit less smooth, but the results are pretty much the same. So this is with arbitrary matching. This is the relative deviation, and again, the order of the allocations, which allocation produces the best result, or the order of the scenarios, which scenarios are more favorable. These are completely the same. It's just that there are some weird things happening sometimes. Well, if we have low number of countries, the effect of country sizes being different can make funny stuff. That's true. But yeah, everything else is pretty much the same. Thank you very much. Any other question? And I promise we haven't discussed that you're gonna ask that. Okay, thank you very much. Both you and online, and I managed to switch this off. Okay.